Let's have a look at the energy of a mass bouncing on a spring. This gets a little bit tricky in year 13, but for now it's not too bad. So we've got our spring. Now, there's a couple of other things that we haven't really talked about, but we will. Firstly, unstretched, stretched. What's the midpoint? The midpoint is an equilibrium point. If the mass is not bouncing, then it will stretch to a certain point, and it will keep stretching until the stretch in the spring, F equals Kx, is equal to the downwards force on the mass, mg. So you can say mg equals Kx, or K equals mg over x. Another way of looking at this with a bouncing mass. Remember that. Often you will need that, all right? Now, so what's x in the situation? The x I used here was just the amount of stretch it has to get it to equilibrium. So if that's the equilibrium point, then there's another x here. Now, you're going to probably have to look at this video a couple of times too. I told you springs, love them, but they are a little bit tricky. But you watch the video a few times, you'll be a bit of an expert on it. Now, at the top, this is where EP is gravity, gravitational potential energy. All right, all gravitational. What's happening in the middle? This is a mass that's bouncing up and down on a spring. In the middle, what you've got there is you've definitely got kinetic energy. You've got some stretch, so you've got some potential elastic. And depending on where you measure your gravitational from, if we measure our gravitational from here, you've still got some EP. So we're measuring our gravitational point from there. That means gravitational energy, EPG, is equal to 0 at that point. We could measure it from anywhere, but let's go from there. So what happens at the bottom? At the bottom, you've got EP gravity equals 0. EP elastic is max. And EK is 0. So top, here, you've got maximum gravitational potential. Middle, you've got a combination of all of them, if you measure your gravitational potential from here. And at the bottom, you've just got elastic. Weird, isn't it? And there's an interchange of these energies as it bounces up and down. And it will bounce up and down forever, unless there are losses of energy to heat and drag. Drag with the air, heat within the metal. But if we could have no losses, we would actually have a bouncing mass that would bounce to the same height forever. All right. Now, you don't know it yet, and we won't prove it yet, but the time it takes to bounce when it's doing this is the same for little bounces or the full big bounces. All right. What we're saying there is the time for the period, and remember, period is always one complete oscillation. To go from a certain position down and back to that same position is the period. And we often use the letter T to define the period. And what I'm saying is, for the amplitude is how big are the oscillations. For small oscillations or big oscillations, the period is going to remain the same. Very important. Now, especially when it comes to those 2.1 experiments we do, you may end up doing them with a pendulum or other such things, or bouncing masses, all sorts of things we can do. But the period of oscillation stays the same for small amplitudes as big amplitudes. What's really going on here, though, is something to think about, is at the point that the forces are balanced, the equilibrium point in the middle, where mg equals kx, the problem is that the energy, the gravitational potential energy, is lost when it goes from this point to the midpoint. Now, the big issue is if all the gravitational potential had gone into the elastic, it would just stop. It would just go, all the energy would have been used up in the elastic. The forces would be equal. It would just stop and sit there. But it doesn't. The forces might be equal, but only half the gravitational potential has gone into elastic. And so the other half goes into kinetic. All right? It's a really interesting thing. And that half I talked about does not depend on the K. Bigger K, it's still just going to be a half. As it continues past that midpoint, we now get to a point where all the gravitational potential at the bottom has now gone into elastic, because as the force got bigger and bigger in the spring, it was able to absorb more and more of the gravitational potential. So it gets to a point here where all the gravitational potential lost, mg2x, has totally gone into the elastic, half kx or half k2x squared. And so at that point, there's no energy left over and Ek is 0. But we got a problem. And the problem is this. Now, in terms of forces, the elastic force is much bigger at the bottom than the weight force, which never changes. So it's not going to sit there for long. It's going to start accelerating back up. So we get this permanent cycle. Listen to the things I've said a few times and you'll understand what I'm talking about. So this is energy of springs.